So, okay, we'll start with VIRTIS, and in this part, the presentation will be divided in two sections. One is this one, and this in this one I will address general concept of the instrument without entering too much detail, of course. And I will talk on the VIRTIS-M in particular, which is the mapping spectrometer, and then there will be a second part with Pierre Drossard with the VIRTIS-H, and also additional information where you can find the data and so on. Okay, so VIRTIS, first of all, stands for Visible and Infrared Thermal Imaging Spectrometer. The scientific team is pretty large. It's composed of 40 people coming from 10 countries, so it's very broad. And I have the pleasure and the honor to share with Pierre Drossard, the PI chief of this instrument. By the way, apart from the formal co-Is in the team, there are a lot of young scientists being formed during the Venus Express mission, and that they got their PhD, and they have really contributing significantly to the results that we have got so far. And also in the progress of Venus science, but also not only because some of them are doing also other job. Okay, just a few words of what is the data coming from VIRTIS. This is an example. You can imagine the data coming from VIRTIS as, for what concerns VIRTIS-M, a stack of many monochromatic images, one on top of the other. Actually, you can consider this as a camera with 864 channels. Or alternatively, you can consider bidimensional images, and for each point of the image, you can get the full spectrum in the range between 0.27 microns up to 5.2 microns. This is for VIRTIS-M. At the same time, we have the field of view of VIRTIS-H, which is about in the center, which provide not images, but spectral information at high spectral resolution. This is the main characteristic, so you can see for VIRTIS-M, as I said, the range is this one. VIRTIS-H is between about 2 and 5 microns. Spectral sampling is 1.9 for the visible part of VIRTIS-M, because VIRTIS-M on its own is divided in two channels. One is visible and one is infrared. Spectral sampling for the infrared is about 10 nanometers, while for H is 0.6. Field of view, total field of view is 64 by 64 for M. H is 0.58 by 1.75 milliradians. And the instantaneous field of view is 250 macroradians by 250 macroradians for M. Of course, for H, the IFOV and FOV coincide exactly. This is a picture just before the integration in Turin in 2004, so many years ago. And you can see here essentially the part of VIRTIS-M baffle, which is this one, is rectangular. And this is the part of the baffle of VIRTIS-H, so the two channels are just below the big radiator, which is white, which is here. And the radiator is able to passively cool down the instrument at a temperature of about 140, 150 Kelvin. On top of this, you need additional coolers, which are on the bottom here, not visible, that are cryocoolers able to cool down the infrared detectors to a temperature below 80 Kelvin. Okay, this is another picture for you during integration on the spacecraft. This is the Venus Express spacecraft, and this is the VIRTIS instrument just in the phase of mounting on board. Okay, just to tell you about the observation strategy, because this would be important if you want to play, as I hope, with the data that you can freely download from the PSA website. Okay, the Venus Express orbit is very elongated. You have a bocenter altitude, which is about 65,000 kilometers. And in this case, we consider what we call a case 2 and case 3, which means nadir observation. So nadir is to have the field of view just looking directly at toward the center of Venus. And during the rotation around Venus, we can have also a close distance from Venus itself in the pericenter. And we use this part here essentially for a spectral mode region. In case 1, case 5, and case 7, meaning case 1 is also nadir, but case 5 and case 7 are what we call a limb observation. So we are not looking straight down to the planet, but just on a side toward the limb. Okay, just since if you are going to download the data, you will need how much data you can get. So be ready to have a good hard disk, enough capacity. This is the number of files for produced till now and forever, since unfortunately Venus Express is not anymore there. So we have 22,000, 23,000 number of raw cubes, which is about 38%. And then this amount of geometry and the calibrated data. VIRTIS-M is clear the concept of cube because, as I said, is two-dimensional in space plus the third dimension. But also H is producing what we call the cube, even if you get just one part of the cube to have just the spectral information. This is also this number of total number of files divided by H, visible, infrared, respectively yellow, red, and blue. Okay, as I said, hard disk, you need 2.2 terabyte if you want to download the full set from the PSA website. So it's really a great amount of data, of which is 62% are fully calibrated data that you can use for your science. Of course, you don't get second level, high level scientific information, but you can have the data that are basically available also to the team. I will now show just a few samples of what you can do with the data. So I do not explain you what are the results and so also because there is a full week of time to explain all the results achieved. So, but just to give you some example of what you can do with the data and how you can use the data. Of course, you can use the data, for example, just picking up one single monochromatic wavelength, in this case 1.7 micron, and you can use the image to study the morphology. In this case, is a good view from the south hemisphere, and the south pole is about here, so you can see the polar vortex in the deep atmosphere at about 47 kilometers of altitude. Combining different images acquired at different time, you can have also dynamics study, and this is a set not geometrically calibrated, in sense not mapped on the planetocentric coordinate system of Venus, but by using these images you can provide something like this, so you can study winds. This is well a rather ancient now paper from Agustin Sanchez La Vega, but still very valid. And by using different wavelengths, in particular, you can study for the 1.74, what I shown before in the images is the winds at the altitude of about 47 kilometers. So, and then by using also the cloud tracking on the cloud top and the day side in this case. Oh, by the way, I forgot to tell you this is the night side. So otherwise you don't get any contrast as much as in this case. And you can get the three-dimensional, let's say, wind measurements. For the cloud top, you get something which is on the altitude of about 65, 70 kilometers. As you can see, there is a strong vertical wind shear as expected, and the winds are about 50 meters per second in the lower clouds, and it can reach 110 kilometers 110 meters per second on the cloud top. Okay, this is a typical sample of spectrum, not the full spectrum, but because this is just on the day side. Above this wavelength is the signal is very small due to the high contrast that you get from the short part of the range. And by picking up a single wavelength, you can get images, monochromatic images with different contrasts that you can use for your analysis. Okay, this is a scheme for VIRTIS-M calibration. As you see, it's a rather articulated procedure. It starts from the loading of the file, of course. Then there is a thermal evolution correction, a correction for bed frames, dead pixels, saturated pixel. Then there is a work on the spectral registration, on the radiometric calibration. Then again, filter and filter and filter, and then you get at the end the calibrated cube file that to which you have access. One important point is that the calibrated data delivered to PSA, so these are freely available through this website, are exactly the same that we are using also for our team. So we do not have any more correction or whatever in our team than you can have from downloading the data on the PSA. Okay, just an additional example in Nadir geometry for case 1, case 2, and case 3. This is an image that we got just 1 day after the Venus orbit insertion in the far April 13, 2006. And as you can see, there is details from the day side, which is on the left side, where you can recognize the features, but also on the night side at 1.7 macron, which are probing at a completely different level of altitude. So there is a level difference in altitude of about 20 kilometers from the left side to the right side. This is also another good example of how you can play with the data. For example, by observing the Venus on the day side and looking at, at the reflection from the sun radiance, you can, for example, study the altimetry by using the CO2 absorption around 1.6 microns. So the deeper is the bands and the lower is the clouds. This was a very successful study by, for example, Nikolai Ignatieff in the past. And as you can see, this was also presented, being presented yesterday by Dima Titov. There is this large depression in the polar region and for a difference in altitude of about 10 kilometers from the equatorial side to the polar side. The imaging spectrometer is very, very interdisciplinary instrument. You can really use the data from an instrument of this type to study from the surface to the mesosphere to the upper atmosphere. So that's why also a large team is needed because of different experience coming from the different parties. This is an example for how we can use the atmospheric windows around 1.05 microns. This is a paper from Niels Müller that should be also here somewhere. And this is a nice correlation with the synthetic map from Magellan. If you assume, it's a little bit complicated to explain in a short time, but if you assume a constant emissivity, you get something which is basically an altimetry of the Venus surface, because you have different temperature coming from different levels. Okay, for the lower atmosphere, there is this good, nice example that also Kong Sang reported yesterday about the CO distribution. And as you can see, the powerful of the investigation is that you can get a global mapping sometime, not always depends on the orbit, but sometime you can get the global map of CO distribution. As you can see, for example, there is an enhancement at around -60 degrees, as was discussed also yesterday. For the thermal structure, using the unfortunately, I'm sorry, it's not very visible, but by using the 4.2 microns absorption features of CO2, you can retrieve the temperature structure of the mesosphere from an altitude of about 65, 70 kilometers up to about 85, 90 kilometers. This is a good example which is reported by Davide Grassi. And as you can see, there is, for example, a nice cold color feature here with a low, very low temperature, and also other features toward the equatorial region. Polar vortex, you can study structure and dynamics. Actually, from a view of the south pole of the vortex at the very beginning, we have got for the first time the 3D temperature distribution of the polar vortex. And by chance, at that time, it was a dipole, as was expected, but I can show you that this is not the usual case, in fact. And you can see, for example, the map of the temperature. Here you can see, for example, some noticeable information, which is the higher temperature in the center of rotation of the vortex. So we have two center of rotation here and here. And also the very, very low temperature of the cold collar with the thermal inversion just around the polar vortex. Okay, this is another example of not a dipole vortex, but is an example actually not of the 3, but even 4 center of rotations in this case. But you can nicely use the, in this case, the 3.8 microns to study the temperature of the cloud top of the vortex. And also you can measure, for example, the geometrical characteristics. You can see the center of rotation differ by about 1,300 kilometers in this case. Okay, another interesting study that you can do is the night glow. And night glow is, for example, in this specific case, for O2 is coming from the emission of 1.27 microns. Night glow in nadir is a little bit tricky because it has to be corrected by 2 factors, essentially. One is the thermal infrared emission from below, from the atmosphere in particular, but also from the surface. But also there is a backscattering from the clouds. So once you have corrected for the 2 elements, you get something like this, which is a pure emission of O2 from the view of the south pole of Venus, and so the equatorial horizon is here. So you can see how it is distributed in the antisolar point, but with a shape which is very complex. This is another case where we have applied, for example, a study of the dynamics of the oxygen emission. You can see a set of images acquired in a short period of time. This was also a study performed by Ricardo Hueso that could be here somewhere. And so all the features are in a way demonstrating that O2 emission is essentially dynamical driven, not chemical driven. For the limb geometry, I will spend a little bit more of how we observe the limb. The limb can be observed with the slit of the instrument, which is exactly perpendicular to the limb, as in this case. And in this case, you get a very nice vertical coverage in one shot, instantaneously in this case. But then it's not the best because the speed of the spacecraft with respect to the relative speed of the field of view with respect to the limb is very fast, and so it's not optimal for this type of observation. But just to give you some example, this is the O2 emission at 1.27. This is the band at 0,0, but also 0,1 at 1.56 here. And you can see the brightening of the limb due to the O2 emission. And this is something that you can get from limb observation. It's another couple of cases. This is inertial, what is called inertial limb night side. And this is tangential limb night side, where you can see that in one single shot, which is one line here, you can get the full coverage in altitude between, say, 70 kilometers up to 200 kilometers or so. Another example is the hydroxyl night glow, and the powerful of the limb observation is that you get, of course, the tangential distribution of the emission that you can correct by using onion peeling or other technique, and then you have the volume emission rate along the vertical direction. Okay, this is another example for the O2 in the visible, and you can see the Herzberg bands and Chamberlain bands and so on. And this is also is a work from Alessandra Migliorini, who is also there in Platea. A special mode that we apply for is limb tracking. This is really, we have used the spacecraft in a way that is not conventional. somehow. We use this one in a way that we are pointing the limb at a certain altitude, keeping the track of this limb with the time, and then using the scan mechanism spanning on the vertical direction. In this case, we can get a vertical sampling of the order of 500 meters, which is quite significant, and the range can cover the full range of the limb without any problem. This is a case for the limb tracking, and you can see, okay, this is true colors images by using these bands 1.27, 1.25, 1.26. We have used a special limb mode, but this is done only for calibration. So I would just tell you the information just for curiosity. And the slit here has been put in parallel to the speed of vector of the spacecraft. In this way, each sample of VIRTIS-M has explored exactly the same portion of Venus as the other samples. This is very interesting for the calibration. In fact, you can use it for the correction of the instrument transfer function. This is a case for the uncorrected instrument transfer function. And this is a case for the corrected instrument transfer function after applying this method. Just the last one is just a curiosity, because yesterday there was a question about what are the true colors of Venus. These are the true colors of Venus. So this has been combined by using the three bands, red, green, and blue, as exactly the proper wavelength. And you get, I understand it's not exciting, but this is the, this is the reality. It's a gray image, which is very, very, I mean, it's beautiful, but it is. Okay, and then I skip for the next part to Pierre. So I don't know, maybe the question we can leave at the end. You can take just one or two questions now.